let's talk about how some ligands could bond to metals. And specifically, we're going to include some organometallic examples in this discussion. So to start off, I have some very simple examples, which is just a sigma donation to a metal. So in this case, we have the hydride, which is just a hydrogen H negative, so it's got 2 electrons, and it's able to do a coordinate covalent bond to the metal, as indicated by this arrow, and that means that it's giving both electrons to the metal, and it forms a sigma bond. Something very similar to this occurs in phosphine ligands. And here I just have the generic R, but it could be benzene rings out here, which would be called triphenylphosphine, phenyl groups, so and 3 of them. And that's a very common phosphine ligand that you see in a lot of organometallic complexes. But again, we have a sigma bond character here. So these 2 electrons are being donated to the metal, and not much orbital interaction from the metal's orbitals back to the ligand. Certainly not in the hydride case, because there are no other atomic orbitals really available to it. And in the phosphorus, most of those are occupied with the bonding to the other carbon atoms here. So that's sigma bonding. Now, when we come over to here, I've drawn a few orbitals on the metal because they're going to interact with our ligand, which is the fluoride ion. Now, I've drawn 2 of fluoride's 3p orbitals. I didn't draw the other one because it's out of plane and it's not necessary to involve that particular orbital to get a good picture of what's actually happening. Now, this is one of the metal's orbitals. It could be the dz squared, or it could be the x squared minus y squared orbital. One of those d orbitals that is aligned with the coordinate axes. If it was the x squared minus y squared orbital, then we'd have a lobe over here and here, but for now I've omitted those for clarity. And similarly, I've drawn one of the either dxy or xz or yz, one of those orbitals. And depending on whether we chose a dz squared or something, it could change the identity of these other orbitals. But again, which particular one it is not super important. So what would happen with this is that we can have electron density being fed in from this p orbital into the metal's d orbital here. And if you know a little something about fluorine, these other orbitals are occupied, or fluoride, right? It has 8 electrons in its valence shell, and all of the orbitals that it has are going to be occupied. So it will also send a little bit of electron density back to the metal this way. Now, the effect of this is that not only the T2G orbitals will increase in energy from the donation in the sigma fashion, the T2G orbitals will increase in energy as well, because there's pi back donation towards the metal. Maybe I should not use back in this case because it's coming from the ligand to the metal. So pi donation to the metal. So this is sigma and pi donation. And over here we just have sigma donation. So just to talk about a little bit about what's going to happen to the metal orbitals, the EG orbitals on each of these will increase whereas the T2G orbitals will be less affected by that because there's not a direct interaction with those particular orbitals. Whereas over here, we have some donation coming back into those, or coming towards the orbitals that are in the T2G classification, and so that will raise that level a little bit. And the net effect of that is these complexes will have a smaller delta octahedral than just simply sigma donation complexes. It's one of the consequences of that. Now, you might let's come down here and let's talk about a ethylene. So a carbon double bonded to another carbon. I have just drawn the carbon pi bond. I did not draw the sigma bond, but there's a sigma bond existing between these two carbon atoms, as well as a pi bond. But the pi bond is the one that's going to interact with the metal orbital, so that's the one I've drawn. In this case, we have electron density in this orbital, and it's going to come back into one of those EG orbitals, either the dz squared or the x squared minus y squared orbital. And that will create a bond. And this is a sigma interaction, but it's coming from a pi orbital. So, but that's not all that can happen. There's a little bit more. And this is something that we often don't think about, but there are other orbitals on here. And one of those is the antibonding pi orbital. That's where these destructively interfere with each other. So I'm going to draw the antibonding orbital on this picture. So what's going to happen is, instead of these pi orbitals or p orbitals interacting well with each other, they're going to repel each other on the carbons. So they're going to get pushed away a little bit from each other. And this one will shade in for the, let's say that one's a negative one, and then this one will be as well. So that way, these two on the same side of the carbon atom are pushing each other apart. Now, one thing that happens is whenever we create a molecular orbital that's a bonding orbital, that's one way to combine the atomic orbitals. But when we combine two atomic orbitals to make it a molecular orbital, we'll make two molecular orbitals. And often we just think about the one that ends up being bonding, which is this one. But there's an anti-bonding orbital, and that's when the two p orbitals combine in such a way that they don't produce a bond, and so they don't like each other. So the shading is on opposite sides, and then the magnets would repel each other. Think of it that way. Now, in this case, that orbital is empty, right? Because carbon-carbon bond, there's electrons in here, but there's no electrons in there. And that's one of the reasons why we don't think about it that often. Yeah, there's no electrons in there, so we don't have to worry too much about it. Well, here comes a metal, and it has orbitals that match the geometry and the polarity of the antibonding orbital. And so the metal can send electron density back into the antibonding orbital and strengthen the bond in between the metal and these carbons, but it will ultimately weaken the bond in between the carbon and the other carbon. So this would be kind of a pi donation. Well, it's coming from a pi orbital, but then you have a pi back donation here. So over here, this is still a sigma bond because it's direct overlap, and then we have a pi interaction coming back. So sigma donation, pi acceptance in this case. Something just like that can occur between hydrogen. So we have the orbital that contains the bonding electrons between H2, and that orbital can send electron density to the metal and create a bond like this. But again, that's not the whole story. We also have an antibonding orbital associated with these hydrogens. And I'm just going to draw these orbitals right up here, just like this and like that. So imagine that the two s orbitals do not want to interact with each other, and we'll just happen to shade them in the correct spot. Now, again, we can have electron density flowing back to the hydrogen. Now, what will happen if a lot of electron density flows back from the metal into these hydrogen antibonding orbitals? Well, if enough of it flows back in, the bond between hydrogen and the other hydrogen will weaken significantly. And you can even take this to an extreme where it's better to draw the metal bonding with a hydrogen, instead of drawing it like this, where this bond is indicating that it's bonding with the electrons in the hydrogen bond here, the HH bond. Another way to draw this, especially when there's a lot of electron density flowing from the metal into the hydrogen, is like this. And this would be the other extreme, where the bond between the two hydrogens is broken, and now there's a bond between the metal and hydrogens. And this can happen quite easily. Now, over here, we could also draw something similar to this, but there is a double bond here, so there would still be another bond between the carbon and carbon. So the two ways of drawing this is just like this, and maybe I'll write the carbons there just so it doesn't look like I just drew a whole bunch of lines on the paper. Or in the other very extreme, this could bond like this, where we still have the single bond because that antibonding orbital has not had electrons fed back into it, but now we have a bond that exists between the metal and the carbon in both locations, and now the double bond here has been reduced down to a single bond because of all of the electron density flowing into the carbon antibonding orbital. This has a name. This is the metallocyclopropane model, and then there's the other model where you have more covalent character in between the two carbons. What would send one towards the other, or one direction or the other? We'll talk more about that in another video, but it really comes down to the oxidation state and the electron availability on the metal. If there is not very much electron density on the metal, it would exist more in this form because the ability for the metal to bond or send density into the antibonding orbital would be vastly reduced. Whereas if we had a metal in a low oxidation state, it has a lot of electron density on it. It would be more likely to exist in this state because it has those electrons to feed in to that antibonding orbital. So this is a brief overview of some of the bonding motifs that we see in organometallic complexes.